ready test.
Haven't touched that yet. It's gonna be this weekend's job. I also have a homework for you that I need to grade, so I'll be thinking about you a lot this weekend. Any of you had a chance to look at the waveguide notes? I sent it to you, right? You've seen the thing. All right. Like I said, I was hoping to get more done on those notes by the time we cover the material in class, but it's taking me longer than I expected. So we're discussing the different possible solutions for the field in the waveguide. And out of the 6 field components, Ex, Ey, Ez, Hx, Hy, Hz, we only work on the E sub z, right? And for the boundary conditions, and we discovered that the E sub z, as stands, can have more than one possible solution depending on 2 parameters that we named m and n. Integers that identify the field pattern on the cross-section. We look at the cross-section here. We discovered that the field pattern must be 0 at the edges here. Tangential field, that is, because we're talking about E sub z, and E sub z is tangential to the conductor. E sub z, this is a z coordinate, this is our x, that's our y, and we chose the broad dimension on the x-axis and the narrow dimension on the y-axis. And the E sub z is tangential on those edges, so it has to be 0 here, has to be 0 there. That's your E sub z magnitude. Let's not say magnitude, because we're going to show polarity. And along the y-axis, we had a similar situation. Again, the E sub z is tangential along all these points, so it has to be 0 here, has to be 0 there. And the equation showed that we end up with sinusoids, because with the zeros, obviously. So we can have this distribution for the E sub z, or possibly a second order of it, or a third order. All these are possible solutions, etc. So we said m is equal to 1. This one here is m is equal to 3, and so on and so forth. And over here, we can have several possible solutions again. N is equal to 1. Which one of these is the real solution? The finite boundary conditions will reveal that to us. But for now, we claim that all these are possible solutions, and we don't know exactly which one will exist, which one will not exist, and how much of each solution will possibly exist. So that's n is equal to 2. Based on that effort, we wrote E sub z and gave it the subscript m and n. Actually, if I say E sub z, that means I can do a summation on the m and the n of E sub z, m and n. And E sub z, m and n, writing that on different lines so it will not appear too long, is equal to a sinusoid here, m pi x over a, sine n pi y over b. And then we had 2 possible waves. e sub z mn plus e to the minus j k sub z z plus e sub z mn minus e to the plus j k sub z z. So put that in, and that's our solution. So over the cross section, we can see this, the product of these two signs, and we showed a special case of 1 and 1. I can show you another case today. For example, let's say we pick m is equal to 3 and n is equal to 2. Let's say 3 and 2 here. That means 0 is here along that line, and 0 is here. So all these are zeros. You have a sign here and a sign there. That means a hump over here, or a mound, if you wish. That reduces to zeros. Likewise, plus and plus will give you another positive field over here. And again, goes to 0 on the edges. Minus and minus give you a plus here. Plus and minus gives you a minus here. I'm going to show that with different colors. So we have x's. And we have an x here with x around it. X here with x around it. Those of you who work with optics recognize fringes that happen in laser patterns. It's the same kind of thing. You can think of these as different fringes. Intensity-wise, these will be all bright spots, and between there will be black spots.
I thought that they multiplied. So why is the bottom middle one a positive instead of a negative?
They multiply, right? So if you work with this one here, that's a positive. It gets multiplied by this one here, which is a negative, right? These are negatives. Well, these are positives. Positive, positive, negative. You see it now?
It's the bottom center one that's confusing.
The bottom center?
Yeah.
Well, that's negative times negative. This is negative. Let me show only the third pattern here. We'll show only the third one, because I'm doing 3 and 2. Let me erase that 2. So that's your 3 and 2. You see it now?
Yes, yeah.
That's negative here, negative there, and the product of the two negatives gives you positive. So that's the pattern over the cross section. You okay with that? Okay. Now, don't forget that this gets multiplied by the z component. So we're assuming that the z is fixed at some positive number here. Okay, if the z goes now negative, obviously all these will flip. So all this, as it goes down the line, this could come to a negative value, so they will flip negative, all that. Right? So the z factor is not shown here. So that's only the cross-section pattern, assuming this bracket here is equal to 1, for example. Okay? Just ignore the z, ignoring the z coefficient. Now, all of these are possible modes. The 1-1 was like this, we showed that. That was your 1-1. There is a 2-1 and a 1-2 and a 2-3 and 3-4 and all these possible solutions. And we get to sum them all. So all these are happening simultaneously. All right? I'm just looking at one solution here, or one mode as we call it. Now, which modes will exist and which modes will not exist And what is the proper values for m and n? We said we have a constraint on those. And the constraint was m pi over a squared plus n pi over b squared. That's your kx squared. And that's your ky squared. Plus kz squared is equal to k squared. Remember that? Which was omega squared mu epsilon. So that's plus k sub z squared is equal to omega squared mu epsilon. And therefore k sub z squared, omega squared mu epsilon, minus this coefficient here, m pi over a squared plus m pi over b squared. It's obvious if I keep changing the m and n, I will be changing k sub z, because that's a constant here. So that means k sub z actually deserves to get the m n subscript. Obviously, if m and n are low, then your k sub z squared is positive. If m and n go higher, m sub n, the k sub z m n could go negative. Right? So for certain values of m and n, I'll say here low, and I'll say here high. Here k sub z squared is positive. Here k sub z squared is negative. As I increase my m and n, the combination could come to a point where this exceeds that and this goes negative. So to see the positive and negative, let's go back to the z solution. I can have, if k sub z squared is positive, that means k sub z is real. I'm going to call it beta, for obvious reason. Because the solution would be, in this case, I'm going to say here now, this is the case of k sub z squared is positive. That means omega squared mu epsilon is greater than the m pi over a squared plus n pi over b squared. Fine. And that range, that means the solution now, this becomes Ez plus e to the minus j beta z, beta mn again, don't forget that, plus e sub z mn negative e to the plus j beta z. If I take either one of those and go back to the time domain, what do I see? I see e sub z mn plus magnitude cosine omega t minus beta mn times z. There must be a phase here, plus some phase. Call it phi plus. Comes from the e sub z. Once I take the magnitude, I get a phase. And we've seen this in the time domain to be a wave that advances or propagates in the positive z direction, right? With a wavelength lambda is 2 pi over beta. In this case, I'm going to add mn. Therefore, lambda will have mn. And there will be a C phase, mn again, which is equal to omega over beta mn. We've done that before in transmission lines, so we get to expect the same kind of thing. It's a wave propagation. And so this one here is a wave that propagates in the plus z direction. And this is a wave that propagates in the negative z direction, which will have the same lambda mn and c phase mn. Same exact thing, just different amplitude. And obviously different phase.
What's the case with the K squared is negative and it's high, and then you have a
This one?
imaginary? Yeah, and you have imaginary KZ, and
Right.
what is that?
We'll do that right now.
Okay,
That's next.
all right.
Just want to make sure that I get no negative reactions before I deal with the negative sign. All right, so let's go to the K sub z squared negative. All right, in this case, K sub z is imaginary. I'm going to call it J alpha. Right? It's an imaginary, so I'm going to call it J alpha. We'll put it there in the expressions. In this case here, this is omega squared mu epsilon is less than m pi over a squared plus m pi over b squared. My solution now is z in square brackets is going to be e sub z mn plus e to the, you do j alpha, and you have a j k z, you end up with what? Minus alpha mn z plus e sub z mn negative e to the plus alpha mn z. Someone would say, actually, you should have the plus here and the minus here. It doesn't matter. Okay, I'll make it work perfect. I'm just going to add a minus here. Okay. All right. Because after all, it doesn't really matter. Because what you see now is no propagation. You go back to the term domain, and what do we see? We see e sub z plus mn, magnitude e to the minus alpha mn z, and you have cosine omega t plus p plus. So you have a wave, yes, but that wave along the z direction is dying, right? It does not have a propagation characteristic. So that wave is not propagating, no propagation, and instead we have attenuation. We call that, we are not using this guide in that mode, and we'll call this situation here a cutoff. The guide is not propagating the waves. So it's obvious that we can write this in terms of some critical frequency here, because eventually let's see, I can use the space here. Okay. I'm going to write this as omega sub c squared mn mu epsilon. I guess I can do that, right? So defining omega sub c squared mn as m pi over a squared plus n pi over b squared, then I can simply write if omega is greater than omega sub c, I have propagation, and if omega is less than omega sub c, I have cutoff. and I can translate that to f greater than f sub c. Again, I have to add mn. Keep forgetting the mn. And f is less than f sub c mn. So there is this critical frequency for each solution. Each solution has its own f sub c mn. If my operating frequency exceeds that, the mode is triggered on. If I'm less than that critical frequency, the mode is non-existent. All right? So let's take an example here. If I were to choose A and B, the X-band waveguide has A of 0.9 inches and B of 0.4 inches. That's the one that you will be seeing in the lab, right? If I work these numbers here, and put my m and n in different combinations. Let's say I'm going to say m is 1 and n is 0. And do the calculations of your f sub c from here. All these numbers are known now. A is known, B is known, m, n known. I can get f sub c. You'll find that the f sub c 1, 0 is 6.5 approximately gigahertz. If I put m is equal to 0 and n is equal to 1, I get f sub c 0, 1 approximately about 13.5 or something like that. Gigahertz. I can't remember the exact number for that. So if I go over the frequency here, that's your frequency axis. Let's do one more. M is equal to 2, N is equal to 0. That's f sub c 20 is about 13.1 gigahertz. You can do 1 and 1. I can't remember the number for 1 and 1, but it's about greater than that anyway. M is equal to, let's write it 1. M is equal to 1, N is equal to 1. F sub c 1, 1 is greater than 13.5 gigahertz. I'm not gonna develop it. So if I go on the frequency axis now, and that's my DC, 6.5, 13.1 approximately, and then the next one and the next one. The 1-0 mode is cut off here, all right? So that's done in blue. So it's cut off here. And then propagation here. That's the 1-0 mode. The 2-0 mode is again in blue, cut off here, and propagation here. to 0 propagation. 1, 0 propagation. To 0. The 0, 1 mode my apologies. (13.5) is a 0, 1 mode. So the 0, that's 13.5 here. That was 13.1. 13.5 is cut off here. That's the 0, 1 mode. Cut off and propagation here. That's 0, 1 propagation. And finally, the 1, 1 mode is cut off here. And propagation there. 1, 1. You look at a diagram like this, and you can tell what's happening as you increase your frequency. The overall is happening, what's happening here now is nothing can propagate here, pure cutoff. And now you start to see the 1, 0 mode up to here. Over here in this short duration here, you have the 1, 0 and the 2, 0. Beyond that, you have the 1, 0 and the 2, 0 and the 0, 1. Up to here. Now you have the 1, 0, 2, 0, 0, 1 and the 1, 1. So as you increase your frequency, you're moving from cutoff to what we call a single mode. Here you have 2 modes, 3, 4, and so on and so forth. Obviously, yes.
What is the FC11 frequency again? Is that just
It's
right here.
13.5,
Okay.
which is greater than 13.5.
Okay.
It's greater than 13.5. I don't have the number, I can't remember it. Now, that order can change depending on your A and B, all right? So it doesn't have to happen this way. If you change dimensions A and B, you may have a different order of your modes, and things may go different. This is our, you do that in blue, this is our preferred operating range. We usually call this the dominant mode. The single mode that happens at the lowest frequency for the guide is called the dominant mode. Because you always have that mode, right? As you increase, you still have the 1, 0 is happening everywhere, right? So it happens here and on. It's called the dominant mode. And obviously it's a preferred operating frequency because we are not sending our signals in multi-modes causing dispersion, as we talked about that before. And we'll talk about dispersion again. We just very briefly, I believe we talked about it, but we'll explain it further later on. So this is the bandwidth of the waveguide, as we call it, right? In fact, the bandwidth for the waveguide is usually smaller than this because we don't want to really operate all the way to the critical frequencies here, right? We usually try to avoid working close to these, and we choose our bandwidth somewhere in between. We leave a margin on either side. This particular waveguide, the chosen bandwidth for that You see 6.5 and 13, we usually will operate from 8.2 to 12.4 gigahertz. Or 8 to 12. All right? That's typically the bandwidth for this particular X-band guide. This is a recommended range for operation, and there's a good reason for that. When you study the losses in the guide, practical-wise now, get to practical aspects. So far, we're not seeing any losses, right? We're seeing a pure, clean, erased it, all right? Cosinusoid with no attenuation. We're seeing our K sub z is simply beta, right? When you put the the practical situation in and work with the losses in the dielectric and losses in the conductor, your K sub z will become complex, and you will have to have some losses in there. So you'll have a gamma. Eventually it will be converted to a gamma, right? But if you work with ideal dielectric, ideal conductor, there's no alpha to the gamma, it's only beta. But it's not this alpha. It's alpha in the cutoff. There will be alpha in the propagation, which is going to be a tiny loss coefficient to accommodate for the imperfection in the conductor and electric performance. So with that in mind now, I can write a few things here, okay?
Professor,
Yes, sir.
we need to 1 over mu epsilon in that omega c squared and n.
Where? Here?
Yeah, you just,
Oh, you are right. Yes, thank you. We need 1 over mu epsilon in this coefficient. Thank you. That's just going to erase it. And the crown would be wiped off, no traces, except for that tape. All right. Any questions before I do some erasing? I want to get back to lambda and what is it? The other thing was C phase, the phase velocity. Okay. So I'm not going to erase that part because I need it. So beta mn was what? It's K sub z, remember? Which is the square root of omega squared mu epsilon minus omega sub c squared mu epsilon. Right? So I can take square root of mu epsilon out, and I can take a 2 pi as well, and I have a square root of, how about if I take omega as well? 2 pi f. I have 1 minus omega sub c, or f sub c, mn over f squared. What's the square root of mu epsilon?
let's see. 1 by
1 over
phase velocity.
the phase velocity in the medium, right? Unguided. If it is mu naught and epsilon naught, it would be 1 over the speed of light in free space, right? Okay, so that's 1 over C phase, I'm just gonna add U. The U here indicates unguided, open space, but not exactly space because we have mu relative and epsilon relative, so that's in the median. In the median without a guide, right? So unguided median. Media filling the entire space, that's your phase velocity there. And that's 2 pi f. I can leave it as omega for now. No, let's keep it that way, all right? Times the square root of 1 minus f sub c mn over f whole square. And that's 2 pi over lambda. So we conclude that lambda mn is equal to what's f over c phase, or c phase or whatever. I have to reverse that, right? So it becomes c phase over f, which is lambda unguided, lambda u divided by the square root of 1 minus f sub c mn over f whole square. So if I were to do lambda mn here in the guide, I'm just going to add in the guide here, right? To distinguish between G and U. G in the guide and U is outside. Is equal to lambda U divided by this. So I need that quantity here, 1 over f sub c mn over f whole square.